This is the last feedback webinar of this year's edition of the course about 3 experimental methods that are to some extent related: low temperature nuclear orientation, NMR on oriented nuclei, and perturbed angular correlation spectroscopy. For those of you who are watching this live, this is last minute, not a live stream. It is pre-recorded a few hours before due to an agenda issue. So that means it is not possible to ask live questions in the YouTube chat, but you can always send an email with your questions. What are we going to do? Well, the 3 methods define the 3 topics of this webinar: low temperature nuclear orientation, NMR on oriented nuclei, and perturbed angular correlation spectroscopy. At the end, there will also be a short recap of the entire course, a summary in 2 minutes, and a reminder about some of the exam-related information for those of you who take the formal exam. In our scheme of nuclear methods, the 3 methods that we will study today are both methods of type 3, so there are nuclear transitions involved. And with all of these methods, what is important is that very often the probability to emit a gamma ray or another particle in radioactive decay, that probability is anisotropic, it's direction dependent, with often the axis of the nuclear spin being the high probability direction. We will not go into the details of this, just keep this as a given that for all of the methods that we discuss, we will assume that the spin direction is the high probability direction for emitting the gamma ray. This is not always true, but in many cases that will be true. This anisotropy in the gamma ray emission has observable consequences once you have an oriented ensemble of nuclear spins. Look at the situation here at the bottom, where we have a nucleus with spin 1, and depending on the orientation of that nuclear spin, depending on the m value, there can be 3 different energies, one of them being the lowest energy. Now we lower the temperature down to the millikelvin region, the same temperature, this is the temperature region where low temperature nuclear orientation plays a role, and therefore at these very low temperatures more nuclei will be in the lowest level, with here an m component of +1, so pointing along the positive z-axis. That means if you take the distribution pattern of the nuclear spins, you will have the pear shape, symbolized by these 2 representations. But because the emission probability of the gamma ray in the radioactive decay of that nucleus is equally likely to emit the gamma ray along the nuclear spin as opposite to the nuclear spin, this means, or this has as a result, that there are as many gamma rays emitted in this up direction than in this down direction. There are less gamma rays emitted in the direction perpendicular to the z-axis. Therefore, if you put detectors around this nuclear ensemble, detectors that count the number of gamma rays per second, then the detectors that are along the spin direction will have more counts than a detector that is in the perpendicular direction. And it's this difference between these two types of detectors, this measured intensity difference, that is related to the anisotropy of the nuclear spin direction. So you can see the orientation of the nuclear ensemble in this detection difference between these detectors. And that is the principle of low temperature nuclear orientation. The amount of orientation will depend on how far are these levels apart from each other. At a given temperature, a strong hyperfine interaction, where these distances will be large, will lead to a larger difference in occupation of the levels and therefore a stronger orientation than if the hyperfine interaction would be much smaller. So this detection in this intensity difference is also related to the strength of the hyperfine interaction. We have discussed in the module about low temperature nuclear orientation a specific example with a neodymium nickel sample, and I asked you two questions about it. First, try to find how the radiation pattern that this sample will emit, how that radiation pattern looks like. And once you know the radiation pattern, then find out which type of hyperfine interaction is responsible for this. Let's look first at the situation and then at your answers. So let us remind what the situation is. We have an neodymium nickel crystal, which is an orthorhombic crystal. This means the three crystallographic, or the three edges of the unit cell have different lengths. We have the 147 neodymium nucleus, which is our active nucleus, spin 5-half. It emits gamma rays with 531 kiloelectron volts. And we apply an external magnetic field of 0.7 Tesla along the A-axis, which is here the horizontal axis in this picture. We then have three detectors, one along the A-axis, one along the B-axis, and one along the C-axis, that look for this 531 kiloelectron volt photons. And now we plot the intensity that is detected in these three detectors as a function of temperature, or rather as a function of inverse temperature. So the high temperatures are here near the origin, the low temperatures are at the right hand side. And the values you see here, they are these inverse temperatures. So this dashed line here corresponds to 40 millikelvins. This dashed line corresponds to 12.5 millikelvin. On the vertical axis, we plot the actual number of counts at that temperature minus the number of counts in that detector at a high temperature, so at 0. So you see the difference in count rate with respect to the high temperature. So the lower the temperature becomes, the more you are to the right hand side of this picture, the stronger the difference, the larger the difference becomes with the high temperature value. And in detector A, this number of counts diminishes. In detectors B and C, the number of counts increases. I should remind here that in the video, on the slide that is visible in the video, this description of what is on the axis is wrong. It's just the other way around. So this has been corrected here, but the axis itself, that remains correct. That was correct in the video. It's the number of actual counts minus the number of hot counts. Well, what did you answer to this? That first question, how does the radiation pattern looks like? One of your answers, we see less intense radiation along the A-axis, because this difference is negative. So along the external magnetic field, less radiation and more intense radiation perpendicular to the A-axis. That is correct. I only would like to know what is the pattern, the orientation pattern that corresponds to that. So this is not concluded from this answer. Another answer, at high temperature there is isotropic emission of radiation, the same in all directions. When you lower the temperature, more light, well, it's not visible light, but at least more photons are emitted in the B and C direction, and less photons will be emitted in the A direction. Again, correct description of what you see on the graph, but which pattern corresponds to that? Another answer, the radiation pattern would be isotropic for high temperatures and would become progressively more anisotropic as the temperature goes down, with less counts in the A direction. Same comment as before, correct observation, but what does it mean in terms of orientation? And once again, a significant reduction in the radiation along the A-axis and an increase in the other directions. Correct observation, but what does it mean? Well, nobody tried to answer what does it mean in terms of the observed radiation pattern. It would be the pancake. The nuclear spins are in that BC plane, therefore turning their least probable side towards the A direction. That is why you have less intensity in the A direction and higher intensity in the B or C direction. Because of the equal emission parallel or anti-parallel to the spin, we don't know in that plane how they are oriented, but we never saw distribution patterns where there is an unequal orientation within a plane perpendicular to the z-axis, so it will be a random distribution in that plane. So the pancake is a good visualization both of the radiation pattern and of the orientation distribution. Then comes the second point, determine from this radiation pattern the type of hyperfine interaction that is felt by these nuclei. And I list here 5 of your answers that gave the magnetic hyperfine interaction as an answer. Not everybody did agree with that. There is also one person who said it should be an electric hyperfine interaction, and another person answered, I think both types of hyperfine interactions can explain this. Well, let's examine what is possible. I give here the splitting of the nuclear levels in a magnetic hyperfine field at the left and in an electric field gradient at the right. Let's assume let's examine for each of these two hyperfine interactions what are the occupations of the different levels at a low temperature. So we have to superimpose a Boltzmann distribution on this. For the magnetic hyperfine interaction, the -5 half direction will be most occupied. So that's a direction parallel to the magnetic field, so parallel to the A-axis. So that would mean if the spins are predominantly pointing along the negative z direction, the negative a-axis, then there would be most photons emitted along that a-axis, so an increase in counts along the z direction, which is not what we observed. There was a decrease in counts along the z direction. So this makes it unlikely that the magnetic hyperfine interaction is the correct answer. Is the pattern that we observe consistent with an electric field gradient? Well, I take here an electric field gradient and a quadrupole moment where the combination of both has that sign that brings the plus minus 1/2 spin at the lowest level. There could have been another sign of the quadrupole moment or another sign of the field gradient, and that would have flipped this picture such that the plus minus 5/2 level would be the lowest one. But that situation would lead to a similar radiation pattern as for the magnetic hyperfine interaction, where also the minus 5/2 levels is the lowest one. So that would not be a good solution. It must be one where we have something different. So in this case, plus minus 1/2 is lowest. So the direction most parallel to the xy plane, that is the lowest energy direction. So that is also the level that will be most occupied at low temperatures. And if most of the spins are pointing as closely as possible in the xy plane, then also their radiation will be emitted in that direction. So yes, the electric quadrupole interaction is consistent with the observed pancake orientation and pancake radiation distribution. So although the large majority of you answered the magnetic hyperfine interaction, it's the other answer. So critically re-examine why you answered magnetic hyperfine interaction and point out to yourself where your reasoning went wrong. Oops. Yeah, and with this, if you understood this story, then you can confidently answer yes to the confident statement, I can read an experimental low temperature nuclear orientation spectrum. Then we come to the second method of today, nuclear magnetic resonance on oriented nuclei. That too is a method of type 3. We had seen nuclear magnetic resonance already before as a method of type 1, so on stable nuclei, not on radioactive nuclei, and there we use radio waves to flip the nuclear spin. In NMR on oriented nuclei, we will also use radio waves, but we will not look at the spin flip. The principle is different. We bring a nucleus in a very low temperature, such that we get this spontaneous orientation of the nuclear ensemble. We go to a full occupation of these lowest levels here. At the lowest possible temperature, we have a full occupation of the lowest level. Now we measure, as in low temperature nuclear orientation, the anisotropy between two different directions. We put a detector in two different directions, and if this occupation of the lowest level has taken place, we will measure a difference in intensity. Meanwhile, we irradiate the system with radio wave photons, and if that energy of the photon does not match this hyperfine splitting, nothing happens. All nuclei remain in this lowest level. But as soon as we do match this energy difference, then we get an equalization of both levels. And therefore, random orientation and no anisotropy in the detected radiation anymore. So if we monitor the difference in intensity between the two detectors as a function of radio wave frequency, we can find that frequency for which the anisotropy disappears, and then we know that this is the frequency that matches this transition. So you measure the strength of the hyperfine interaction as a peak in your spectrum. You change the frequency, and at one frequency suddenly something happens, and once you are beyond that frequency, you're back in the old situation again. Such a measurement is always much more sensitive than what we had before with low temperature nuclear orientation. Here, the strength of the hyperfine interaction is related to the curvature of this line. The larger the hyperfine interaction, the steeper this curve will be. But you can imagine, you need measurements at different temperatures, and if your data points are a bit to the left or to the right, that could slightly change the curvature of this fitted line. So this is much less sensitive. One bad data point can change your fit and can change your conclusion about the hyperfine interaction. NMRON, because it measures peaks, is much more precise. A question that people sometimes ask at this point is, how can it be that NMR is a type 1 method and NMRON a type 3 method? Well, I hope you understand now. In both cases we use radio waves. For NMR, that's the only thing. You look at the absorption of your radio waves, and when you have more absorption, then you know, okay, I have matched the transition energy. You need quite a lot of nuclei for this, because you have at room temperature only a very weak inequality in the distribution of the two hyperfine levels. With NMRON, you look at radioactive decay, so you don't detect directly the absorption of the radio photons. No, you look at anisotropy in a radioactive decay, and when that anisotropy disappears, then you know that you have applied the right radio frequency. So the detection is totally different. For NMR, you detect the radio wave photons. For NMRON, you detect the photons that are emitted in the radioactive decay, and their anisotropy changes if you match the radio frequency. So they are indeed belonging to two different classes. The exercise about NMRON was this example of a measurement where you have 91 strontium nuclei and therefore strontium atoms that are included as substitutional impurity atoms in a BCC iron matrix. You apply an external magnetic field to this of 0.2 Tesla, 0.4 Tesla, 0.6 Tesla. And then you do an NMRON experiment, so you scan the radio frequencies. You observe a peak, a resonance, and that peak shifts to the left, shifts to lower frequencies if you increase the external field strength. The question is, from this experiment, can you deduce the sign of the magnetic hyperfine field? And This is related to the confidence statement, I can explain how the measurement of a magnetic hyperfine field as a function of the applied field can give information about the sign of that hyperfine field. You see that not everybody feels totally confident about this. Well, there was an issue with the forum here. Somehow they disappeared, and well, I should fix that in the course site, but it was too late for your work. So some of you submitted their answers in different ways, and thanks for that. So I show here one of the answers where it is said the derivative of the resonance frequency with respect to the applied field, that is related to the sign of the hyperfine field. If that derivative is positive, the hyperfine field is positive. If that derivative is negative, the hyperfine field is negative. The conclusion, therefore, for this case would be that the hyperfine field is negative. Well, that is true. The answer is correct, but I would like to have seen a general proof why that relation with the derivative is correct, because that is not something we specifically derived in this course. So I'm searching for a different argument. And I need to check something, because there is quite a bit of extra sunlight coming, and that may interfere with the camera. Let me see. Yeah, this is a bit better. Another answer, the experimental observation shows that the resonance frequency decreases with increasing external magnetic field. That's correct. This means that the hyperfine field is negative. When we increase the strength of the external field, we counteract this hyperfine field more. So, therefore, here the hyperfine field has to be negative. And that is a correct answer. I see from the answer here that you have the right argument, although I wouldn't say that the argument is totally clear from this text. If you didn't understand it before, you may not understand it as well having seen this text. So what is the actual argument? It's this slide that we have seen in the module about the magnetic hyperfine interaction, where it was visualized what the sign of the hyperfine field means. It gives the orientation of the hyperfine field, the magnetic field at the nucleus of an atom, with respect to the atomic magnetic moment. So the electron cloud has a global magnetic moment that is oriented by an external magnetic field, a small external magnetic field. That is why we apply these small fields here. And if the hyperfine field is oriented opposite to that magnetic moment and therefore to that magnetic field, then we say it's negative. If it is positive, then it's oriented parallel to the applied field and to the atomic moment. Usually, the hyperfine field is much larger than these small applied fields. So if we have a strongly negative hyperfine field, like in the case of iron, something like -35, and for strontium, so you measure at the strontium nucleus in iron, that will be a different value, but typically in the order of magnitude of -10 Tesla or more. So we have a strongly negative hyperfine field. If we apply a small external field, that is then, if for a negative hyperfine field, that is pointing in the opposite direction. So the actual field at the nucleus will be the sum of this negative hyperfine field and that positive applied field. If we increase the applied field, then that sum will be a bit less negative. We still have the large negative contribution that is partially cancelled by that small positive external field. And now that positive external field becomes a bit larger, so it cancels a bit more. We are left with a still negative total field, but a bit less in value than before. So indeed, our effective field, the effective splitting of the hyperfine levels, moves to lower values. So the sign of the hyperfine field is in the direction of this resonance. If the resonance moves to the left, to lower field values, then we have a negative hyperfine field. If it would have moved to the right, then the hyperfine field and the external field are always helping each other. You have to add two positive numbers, then the field would have been positive. So that is the way how you can deduce this from the experimental data. Now we enter perturbed angular correlation spectroscopy. Again, a method of class 3. We have nuclear transitions. We even have two nuclear transitions in the case of PAC. The tagline that I entered there is the ID of PAC. That is, we want to mimic strong nuclear orientation, but not at very low temperatures. No, we want to mimic this at room temperature or any other temperature. So what is the ID? You have a collection of nuclear spins. You have a detector labeled 1 or start. And if that detector sees a photon in a two-stage nuclear decay, it's a gamma-gamma cascade. So if it sees that photon, then you can say on average this probably comes from a nucleus that is pointing in the direction of this detector. Not always, but generally spoken, there will be more nuclei that are pointing in this direction and emit their photon into that detector than nuclei that are pointing in a totally different direction. So if you would be able to continue your experiment only with those nuclei that have emitted their photon in the direction of detector 1, then you would effectively work with an oriented sub-ensemble. Well, this can be done by starting a clock whenever detector 1 sees that first photon, and then you look with detector 2 at the second photon in the cascade. And that detection would stop the clock. So you measure the time difference between the emission of the first photon and the emission of the second photon. And if that time difference is within, say, 5 times the lifetime of that intermediate level in the cascade, then you know that it is very likely that both come from the same nucleus. If you do that for this kind of setup here, a static situation, so we assume so far that there is no hyperfine interaction, what would you measure if you start the clock with detector 1 and then stop the clock with detector 2 or with detector 3? So you measure here the time difference between detector 1 and detector 2, and here the time difference between detector 1 and detector 3. So I asked you, in both cases I claim this is an exponential decay. Why would that be? Some of your answers, well, basically you say this is trivial because you measure here the lifetime of the intermediate level, and this must follow an exponential decay. That's what radioactive decay does, and that's completely right. Second question, the curve here for the 1-3 detector combination is higher than the exponential curve for the 1-2 detector combination. Why is that? And here your answers are, well, one answer where there is a bit of confusion. So I thought that due to geometrical reasons, angular momentum would prefer both gamma rays to be along the same direction, but I'm not sure. After having seen the explanation in the video, I don't get the time factor. I don't get the role of time here. Okay, let's keep that in mind. See what the second answer says. As we saw in low temperature nuclear orientation, decay happens mostly in the direction of the spin or the opposite direction. So this would cause a higher count rate in this case as well. And indeed, that's the correct reasoning. So the clock is started by photon 1 that is emitted in the direction of detector 1. That therefore means on average a spin that is either pointing towards detector 1 or pointing towards detector 3. There is, after that emission, the nucleus that was in a high state is in a lower state, the intermediate state of this cascade, where you have gamma 1, gamma 2. So the nucleus is, after the emission of gamma 1, it enters the intermediate state, and after a while, depending on the lifetime of that intermediate state, it will either emit the second photon in the direction of detector 3, most likely, as the spin is pointing in that direction, or, less likely, but not impossible, in the direction of detector 2. So you will have more counts in the 1-3 emission than in the 1-2 emission. And that is, if we go back to these pictures, that is why the 1-3 exponential curve is always at higher values than the 1-2 curve, which in these two answers here on the screen has been correctly identified. So where is the time involved? As was asked in this first question, it's just the lifetime of that intermediate level. No hyperfine interaction yet, that will come now immediately, it's just the lifetime of that intermediate level. Now we enter the situation where there is a hyperfine interaction, and there we have seen that in PAC you will have an oscillating function on top of that exponential decay. So I go one page back to this picture. If there is now a hyperfine interaction, assume the easiest situation that there is a magnetic hyperfine field perpendicular to the screen, then the magnetic moments or the nuclear spins will start to precess about the axis of that magnetic hyperfine field. So these spins here would rotate in the XY plane. So after a while, this nuclear spin would point to detector 2. And at that very moment, there would be more 1-2 counts than there would be 1-3 counts. After a while, the spin will point in the direction of detector 3, and at these moments you will have more 1-3 counts again, and so on. So you will alternate situations where 1-2 sees most counts and when 1-3 sees most counts. And how quickly these situations follow each other, that is related to the precessing speed of these nuclear spins and therefore to the strength of the hyperfine field. And there are two ways, two visualizations of the interaction of a magnetic field with a magnetic moment. Either you express this in energy levels and you look at the energy differences between the different levels, or you look at the precession speed, where there is the classical precession of a magnetic moment vector about a field, and the frequency of that precession is related to the energy difference between the levels by Planck's constant. Planck's constant times the frequency is the energy difference between the two hyperfine levels. So that's how these two pictures match. So by measuring that frequency of that alternating pattern, you measure the strength of the hyperfine interaction. And that is where this next question is about, that oscillating function that is on top of the exponential decay, and which in a measurement, well, you remove that exponential background such that you can only look at the oscillating function. That is where your information is located. So in the experiment you have that oscillating function, and I asked you how would that function look like in the two limiting cases where you use PAC to detect a very small hyperfine interaction and one where you want to detect a very large hyperfine interaction. In both cases the experiment will become not sensitive anymore, but for two different reasons. Why? How? And well, one possible answer, somebody writes, I think in these limiting cases for a very small hyperfine interaction, the oscillatory behavior would become very small and hard to distinguish because the peaks, so I think the bumps in the oscillation are really low and it would be hard to measure such a frequency. If I interpret this answer as how I think it was meant, you mean that the amplitude of the oscillation becomes small and that therefore it is difficult to measure the frequency. That is not what happens, because think about these two pictures. A small hyperfine field, that means a very slow rotation, very slow precession of the nuclear spins, and therefore it's not the amplitude that is affected, it's the frequency itself. Planck's constant times the frequency is the energy difference between the levels. Small hyperfine field will mean a small energy difference, so also small frequency. So we have to focus on the frequency, not on the amplitude. And here I put two answers that give the correct answer. And so if you have a very small hyperfine interaction, then that frequency omega or nu is really small, and the decay of gamma 2 will almost always happen long before the spin has been pointing towards detector 2. So rather than measuring an oscillating curve, you will still measure an oscillating curve, but with a frequency that is so slow that it will almost look like a constant, and only for very long time intervals, much longer than you are able to measure, you would rise to the first bump. Well, try to fit a cosine function through a set of data points where you have only the very beginning of the cosine function. You can understand that you will not be able to fit to determine the correct frequency. On the other hand, if the hyperfine interaction is very large, then you will have a very rapid oscillation, and then it depends on what is the resolution by which you can measure these oscillations. You will always have a time resolution in your detection. So maybe I can measure a data point every nanosecond or every half of a nanosecond. But if my oscillation would be so fast that within that 1/2 of a nanosecond you would have had 10 oscillations of the function, then you cannot see these 10 oscillations. I have an example here of what that means. Imagine you can measure data at every time where there is such a red cross. Well, if you do that to measure an oscillating function that has a frequency such that you can measure several data points within one period of that function, that is fine. But if you have a function that oscillates much faster, well, see what happens. You would measure at the same, you would measure at all of these red crosses, and rather than measuring that fast oscillation, you do a ghost measurement. You seem to detect a slow oscillation, the same as you had here, but it's not real. It's an artifact of sampling a high frequency with a limited time resolution. In signal theory, you may have heard this before. This is aliasing, a non-physical low frequency signal that appears due to a mismatch in sampling. So that limits the possibility of detecting very, very high hyperfine interactions with PAC. Well, this was the picture that summarized what I said before and what was also discussed in the video. It's this oscillating pattern superimposed on that exponential decay that leads to the hyperfine interaction. And you may have noticed that this explanation is a very classical one. So I use precessing nuclear spins in an applied field. That's a classical representation of the quantum picture. And in some of the previous topics, say in Musbauer spectroscopy, I emphasized that we should not overuse these classical pictures. So isn't it possible to discuss PAC with a sound quantum approach? And that is possible, and I just give the bottom line of the argument here. We have a hyperfine interaction in this intermediate level, so micro EV differences between these levels, and we measure the first and the second photon, but without particular energy resolution. We need to be able to distinguish that they are the first photon and the second photon. So, but if we know this within a few EV, or sometimes even within a few kilo EV, that's enough. By no means we detect these small energy differences. We don't detect the very small micro EV differences between this photon and this photon. Therefore, we do not know which of these three paths the process has taken. It can be any of them. And you hear it from the formulation. If you do not know which path a quantum system has taken, it means it has taken all of them simultaneously, and there can be interference between these paths. And the oscillating pattern in the observed coincidences between the detectors 1, 2, and 3, these oscillations, these are the interference. This is the result of interference between these different quantum paths. So you can interpret PAC also as an entirely valid quantum phenomenon with interference between different paths. And that avoids the classical interpretation of precession, which has its limitations. You cannot really explain all details of PAC just with that classical precession. In the module there was also an optional part about an application of PAC, an old but very nice story where PAC spectra are used to unravel what happens with the behavior of individual atoms that are put on metallic surfaces. And the story is a good illustration of the power of these methods. It takes a lot of experiments in very controlled circumstances, here with very controlled annealing temperatures. But if you do that, if you go through the trouble of doing all these experiments, you can deduce from that how individual atoms behave on a metallic surface as a function of temperature. And that is something very powerful. There was in that optional module also an optional task. And well, let me repeat what the task was. If you have a nucleus with spin 5 halves that is split by an electric field gradient in this particular pattern here, well, the energy differences between these three levels, that will be the frequencies that appear in the PAC curve. This is something we did not prove or deduce. That is something you should take here for granted. So, more specifically, if we have an actually symmetric electric field gradient for a spin 5 half nucleus, we will have these three frequencies corresponding to these three energy transitions, and we deduced for spin 5 half that this energy difference, so related to omega 1, that this is exactly 1/2 of this energy difference, and the sum of both is the third energy difference, which must then be 3 times larger than omega 1. In other words, the three frequencies that are involved are harmonics. They are integer multiples of each other. This is only true in the case of axial symmetry. If you have a non-actually symmetric field gradient, you will see something different. But first I show some of the curves that you and other people have generated. So if you take that for granted, that these frequencies are the three frequencies you see in your PAC spectrum, and these are harmonics of each other, so twice the ground frequency, 3 times the ground frequency, then you get this type of very periodic pattern. An oscillation with the first frequency, and then this typical structure on top of it. If you see this, that will always be in PAC a reflex. Aha, this is an actually symmetric field gradient for spin 5 half, which is for PAC the most often situation. If you have no axial symmetry anymore, then you still have the same three frequencies, but due to the change in position of these lines, they are not exact harmonics anymore. So your frequency 1 will not be exactly 1/2 of frequency 2. Still, their sum will be frequency 3, but the harmonicity is broken. And therefore, so I repeat here on top of the screen 2 examples of the curves with axial symmetry. If you break the axial symmetry, then the curve becomes much less periodic. in the end, if you measure for long enough, it would become periodic again, but you usually do not get there. So the part that you can observe will look like as a non-periodic curve. So that's the signature of removed axial symmetry. So one possible answer to that question in words would have been, if we don't have axial symmetry, so if we don't have these integer multiples, then we don't have a nice and clean periodic function, but rather a superposition of 3 cosines with, well, not random frequencies, but definitely not harmonic frequencies. And that leads to a non-periodic final pattern. That concludes the discussion about PAC. And as this was the last module of the course, I would like to add a few last words to the course. It's a pity that this year I cannot do this live. And first, I would be interested in your feedback. People from Ghent University, from Antwerp and from Brussels, if they participate in the exam, they will get a separate feedback form. So if you are from one of these 3 universities, you should not care about this. But if you are either from another Flemish or Belgian university, or from a university anywhere else in the world, or in no university, just a volunteering student that has no affiliation, that's possible too. In all of these cases, please go to the QR code or to the link that you see here and fill out some feedback about this course. This is information I use for the next years to keep fine-tuning the content and the way of presenting. Content-wise, I would like to summarize in 1 or 2 minutes the basic information that I tried to convey with this course. So the next minute is what I hope that in 30 years from now you will still remember about hyperfine interactions. And that basically is the 2 very important pictures. If you remember these pictures and if you remember what they mean, then the goal of this course has been reached. The very important picture number 1, that were all the energy scales that are involved in a system of nuclei and electrons, where you have energies related to the nuclear state. For every nuclear state, energies related to the state of the electron cloud. For a given gross description of the electron cloud, a fine structure that is related to how the orbital and spin angular momentum of the electron cloud are related to each other. And for a given of these fine structures, a hyperfine structure that is related to how the nuclear spin is oriented with respect to this total angular momentum of the electron cloud. And every time the energies that are involved, they are different, from very large kilo-electron volt to mega-electron volt, over electron volt and milli-electron volt to micro-electron volt. The very important picture number 2, that was a reduced version of the very important picture number 1, where we show here at the left hand side all these lines are fine structure levels, and at the right hand side we show hyperfine levels. And now we look at transitions between hyperfine levels. If we have transitions between 2 hyperfine levels that belong to the same fine structure level, then we have our experimental methods of type 1. If we have a transition between hyperfine levels that belong to 2 different states of the electron cloud, Then we have methods of type 2. And if we connect hyperfine levels that belong to the two different states of the nucleus, so if we have radioactive decay involved, then we have our methods of type 3. So if you remember and understand these two pictures, then once again the goal of this course has been reached. Then I should congratulate everybody who did reach this module, who did reach this end of the course, because I know it's quite a bit of work that is involved. So you have to do an effort to get to this point. And well, really congratulations if you succeeded to do that. Even more so if this was a course that you took as a volunteering student, so if you get no formal credit for this. That makes the effort even more special. For those of you who belong to Ghent, Antwerp or Brussels universities, the exam date has been fixed by the faculty. It's May 26 at 1 o'clock. In the Technology Park campus, building 46, room 2.3. I will also send a separate message to all the students who are involved in this, also with a sample exam of one of the previous years included. For all other students, there is no formal exam and therefore also no formal credit. But if you want an unofficial certificate, where basically a document in which I say that I have observed in the logs of this course that you have done all the tasks that are required from this course. And although there was no exam and although there is no official relation between you and Ghent University, well, I can testify that this was the case. Well, if such an unofficial document is meaningful for you, then you can send me an email and ask for it. And the course site itself, that remains available, well, as long as I can foresee the future. So there are no plans to shut down the site. Nothing has eternal life, especially not on the internet. But for the foreseeable next years, the course site will definitely remain available. We have some plans to transform it in more languages, in many more languages. There are AI tools that promise that they can be able to do this. So if next year you would like to take this course in Hindi, there is a chance that this is possible. And not only in Hindi, also in Spanish, in Finnish, or whatever language you can imagine. No promise, no guarantee, but we're working on that. So with this I say goodbye to all of you. If you are in that target group, please put your comments in the feedback forum, and for the other people, see you later this month in the exam. Bye bye.